each moved it. All right, you want to say hello to everyone?
Hello.
Hi, everybody. There you go.
Hi. Hello.
Slackers.
All right.
People who are slacking off.
You know it's a
Shut
video.
up.
All right. So,
I was in there for like.
Oh, Sophia, stop it.
Taylor series. Ready? So,
That's like
it's no different than the stuff we're doing right now. A Taylor series is a fancy type of power series, okay? The first thing to realize, I'm going to have to write really big so the video can read it. So, like, when I write, like, absurdly large.
No, it's like inverse.
No, it flips it when you check that, right?
Yeah,
Alright, so, Taylor series.
I love that.
It's
Alright.
actually inverse.
You got pull it closer. Finally,
No,
we have
what is
100%
it?
Don't worry about it.
Alright. Taylor goes last. So Taylor series is this is so funny. Taylor series is just a type of power series. Okay? It's a specific type of power series that we're going to use to model functions. Right? So the idea is, let's say I had some function f of x, right? So back to like take a break from all the series stuff for a second. And we have some function f of x, and it's doing something, right? So it's some like curve, right? We've already talked about the idea that like if I wanted to find a point on the curve, right? And let's say I'm at some point A, right? This would be what? What do we call this? No tricks here. Just f of a, right?
oh.
So that's f of a, okay? Right? So we know the y value at a, right? So if I wanted to approximate this function, and let's say I don't know exactly where the function goes, but I do have a derivative, right? I could use what to approximate where the function is? Could I use the tangent line?
Yes.
Yeah, right? So I could use the tangent line to approximate. And how would I write the equation of the tangent line?
Like
Point
the
slope.
yeah,
Point slope. So this would be whatever.
Y minus f of a.
Yeah. Yeah, so it's going to be y minus f of a is equal to the slope. So we would call the slope f prime of a, right?
Yeah.
Times x minus a. Yes? Or rather, and the way this gets fun is, I'm going to add the f of a over. If I started at f of a, right, and I added a derivative times x minus a to it, right, that would be an approximation. That would be that tangent line. Yes? Yep. Right? So f of x, our function, is approximately that, isn't it? Which means if I moved a little bit away from a, what would happen? Okay, but if I moved just a little tiny bit away,
not that
say
different.
over an interval where these two things converge together, right?
Oh my god.
Right? So if I move just a little bit away, the point on the curve and the point on the tangent line are still going to be pretty good, right? Now, could we do better?
Yeah.
So we've done tangent line approximation, right? We even did Euler's method where we would take, instead of using just one tangent line, we do a bunch of tangent lines that follow the derivative, right?
Yeah.
But what if instead of just matching slope, what if we matched concavity? So what if instead of doing a tangent line, we did a tangent parabola?
What if we make it
What if we didn't?
Okay. So what if I do a tangent parabola? Well, how would I find, what would the tangent parabola have to match up with? The concavity. So we would need the second derivative to match, right?
Yes.
So if we're finding this, we need the second derivative to match, and we also, the equation would then have squared in it, wouldn't it?
Yeah.
So what starts to happen as we build this thing out is we're actually going to look at the second derivative. And the second derivative at a, so here's our slope, here's our concavity. I don't know why I just said that weird, but I'm on camera, so I'm feeling nervous. And the concavity is going to have to be multiplied by something squared.
Why do you just add it up?
I'll explain that I don't have time today. I'll explain that later. Just trust me for now. we're running out of time here. All right. Now, the problem is, if I actually plugged in A here, what would happen? This is good, actually. What would happen? I would get 0 and 0 and f of a. Oh, that's right, of course. If I move a little bit away, now I'm missing a piece, though. Because if I actually took the derivative, if I'm trying to make this match f of x, what is the actual second derivative at a? Well, it would be f prime prime of a, wouldn't it?
Mm-hmm.
Well, to take the derivative of this, if I took the what would f prime of a be right now? Using my approximation.
F prime A plus F prime
The
prime.
derivative of f of a would be what? 0, wouldn't it?
Oh, right, because it's gone, yeah.
Right? And then the derivative of this is to the first power, would be,
F prime prime.
No, that would be.
it would just be the coefficient, which would just be f prime
Oh,
of
right,
a.
we'll take derivative, yeah.
Right? And then over here, it would be, the derivative would be
F prime.
2 f prime prime of a times x minus a to the first, wouldn't it?
Yeah.
And then if I plugged in a, if a goes in there, this becomes 0, and now my slope matches. Great. That's what we wanted. See how that works?
Mhm.
Right? By plugging in a, the slope matches, so we can go a little further. But when I take the second derivative using the approximation, this is still going to be 0. This is now a number, so this is also what? 0. When I take the second derivative now, I've got 2 f prime prime of a, don't I? But that doesn't match. So what we have to do is back up here, divide it by 2. Because if I divide it by 2, those 2's cancel, and now it works. It's not really a kicker, it's just I'm trying to build the perfect, what I'm building is a tangent parabola.
So do you...
But we can do better, people. I know this seems a little confusing, but eventually we're just going to get to a formula. We can do better. We could use a what? A cubic.
Like a journal.
Yeah, what if I used a tangent cubic?
How about milk?
Then you just oh
Right?
compare derivative.
Yeah, so, okay, sort of. So what, in order to get a tangent cubic, I would need it to be what? Match the third derivative. So what if I added another f prime prime of a, and make that x minus a cubed?
Divided by 3.
And now I would have to divide it by 3, because to get the third derivative, I would have a 3 pop down, but I'd also have a 2 pop down, wouldn't I?
Divided by 6.
So it'd actually be divided by 6, or 3 factorial.
What do I see?
Oh, what?
What if we just did this forever?
Infinite
What if
series.
we just made an infinite series that's created by the coefficients of the series being the derivatives divided by the number of the term factorial, and then you just keep going out, because we could get better if we made it 4th degree, or 5th degree, or 6th degree, or 7th degree.
Oh, okay, okay.
It's also centered around x equals a, right?
And it's centered at x equals a, exactly. So this is how we build a Taylor series. A Taylor series is just, can you see over here, I guess. Sorry, Soul. So a Taylor series, the idea is that any function f of x will actually equal, right, some f of a. This is really, if you really want to be careful, f of a is actually times x minus a to the 0 over 0 factorial.
0 factorial
Which
is
is
1.
1. Plus f prime of a times x minus a to the first, and that's over 1 factorial, which is also 1. Plus f prime prime of a times x minus a squared over 2 factorial, plus da 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 da, all the way out here until we get to the term, which is really important, which is to say all of these, I'm running out of room, all of these are just the sum as we go from 0 to infinity of the nth derivative, which we write like this, at a divided by n factorial times x minus a to the n. And this is freaking awesome.
Wait, is that n equals 0 always?
That's a bracket.
Is it a curly bracket?
No, it's just me being a curly bracket.
Does it always,
It's a bracket
does it always
style.
begin with 0?
What?
It doesn't always begin with 0 or
Wait, I can't.
Well, yeah, it's going to start at 0 because that's how we start, because we're starting with f of a.
start at 1.
With this, we're always going to start at 0.
Is that times x minus? So it's like
It's times x minus a. Now, this is just a power series, just like we've been dealing with, just like we just had a test on today.
Wait, so does this
Right.
converge?
Sorry for the double class day. People that had the test today.
Oof.
A little rough on you guys. I
Stop
appreciate it.
it. Don't flex.
But you guys have first period free tomorrow, right? So you get
No, it's
Yes, I was like, it's good.
Oh, yeah, fourth period free. There you go. Warm up for
I
good
have
practice.
first period free
Alright.
too.
I have first and fourth and fifth.
Alright.
I'm gonna
Yes, question.
What does it mean by centering at A?
Alright, so what does it mean by centering an A, right? That means that we know if we plug in A, what happens?
It's like the correct thing.
You three cannot do this to me. I'm on video. So,
Natalie, your face is
so if I plug in A, what's going to happen?
0.
Yeah, I'm going to get 0. Well, really, I'm going to get f of A.
Yes.
You go back to the first term, it's just going to be that,
Yeah.
right? So the issue becomes, can we move further away from A, right? Can I move in a direction where I could actually go further? Well, let's look at how this, so often we've been centering things at what value? Where's it usually easiest to center things?
0.
Yeah, it's always easiest to center things at 0 because it's easy to plug 0 in, right? So when we plug in 0, if you're centered at x equals 0, then we get a special name. That's called the Maclaurin series. So all these are just fancy names. Okay, if you see the word Maclaurin series, all that means is you're centered at 0.
Wow.
You're late.
Welcome.
Sorry.
Level.
Is there only one like Charleston, Mr. Thompson?
Somebody, yeah, we already got that.
Really?
It's recording, by the way.
Jeez.
Ugh.
That's annoying.
Oh.
I should-
It is a good joke, though.
I should have come earlier.
Yeah, look at you, let's stay in the ranks and
All right.
into the whole 30. I see you.
So, let's see what happens if we use an actual function.
Yeah.
All right. So, this is going to be the important thing. All right.
Wait, sorry, the brackets mean the derivative of?
Yeah. It's the nth derivative. Like it's how many times you take the derivative. So like if the n is 0, then you don't take the derivative. If n is 1, then you take 1 derivative.
Correct, correct.
Basically,
All right.
the first term in this series is
What's this sound? We'll go back to it.
Correct. All right. Let's look at a series that's that's not too bad. So, hi Johnny.
That's not
So, let's say I have f of x is equal to 1 over 1 plus x. Okay?
So funny.
Now, I do this one specifically because this is one we're going to need to know. Alright? So, this is one that we're going to learn pretty well. So, let's center it. Let's do the Maclaurin series.
That's huge.
You're huge.
Oh!
That's not
Destroyed.
I meant like muscle. So, Maclaurin series,
Thank you.
that means it's centered. I meant brain power. It's centered at x equals 0.
Yeah.
I just got that's on video.
Yeah, you should probably edit that out.
It's got record.
I'm gonna get fired because of this. All right, so let's find the Maclaurin series centered at 0. All we have to do is start listing the derivatives, and what you'll notice is that the derivatives actually become pretty nice. So let's look at f of x. So f of x is 1 over 1 plus x. So what is f of 0? 1. So that's going to be the first term we need. We're just going to list all the terms we need. What's the derivative of this function?
ln of 1.
Negative 1 plus x.
Yeah, this is 1 plus x to the negative 1, right?
Yeah.
So this is going to
Oh.
be
Negative 1 over 1 plus x.
negative 1 plus x to the negative 2,
Two.
right? And what's f prime of 0?
Negative 2.
Negative 1.
No, it's just negative 1, isn't it?
Yeah.
Just plug in 0.
Oh.
Don't make it, it's not that hard, just plug in 0. All right, what's f prime of x?
2 times
Well,
1
the
plus
2 is going to go
x.
to 2 times 1 plus x to the
Negative 3.
negative 3. What's f prime of 0?
0.
Oh, it does.
Just plug in 0. What do you get?
2.
2. All right. What's f prime of x?
Why are you doing
Is this an alternating?
What?
Is this an oscillating or?
Oh, negative
So
6.
it's going to be negative 6 times 1 plus x to the
Negative 4.
negative 4. Now, does anyone notice anything about what's going on with the coefficients?
Wait, that's
They're
not
alternating. That's
That's
true.
up to.
That's
up to.
Negative
That's negative 6.
Sorry.
Oh, man.
What are these numbers? Well, this is 0 factorial. This is 1 factorial. This is 2 factorial. This is 3 factorial. Because what happens each time is you're multiplying by 3. Right? It's just that they're alternating. So that's negative, that's negative. What's the next one going to be? Guess what the fourth derivative of 0 is going to be? By the way, we just start writing 4. We stop with the dashes.
Oh.
Is this still recording? It's not showing you.
It's gonna be
Hi.
Oh,
Oh, it's still got a green light.
Green light.
But I think your joke was still recorded, by the way.
Yeah, I know. Yes.
Nervously off base.
So what is the next one going to be?
4.
4 factorial. What's the, et cetera, et cetera, et cetera, right?
Yeah.
So do we start to see a pattern there?
Yeah.
Yeah.
So we can now build the series. So I claim that f of x is going to be the first term, f of 0, which is 1, plus the second term, the first derivative term, which would be negative 1 times x. And it's just times x because we're doing x to, it's really x minus 0, right? So again, our Taylor series, our Maclaurin series over here would be, I forgot to write this down, f of 0 plus f prime of 0 over 1 factorial times x to the first plus f prime of 0 divided by 2 factorial times x squared plus f 3 derivatives of 0 over 3 factorial x cubed, etc. Right, so that's what we're doing right now, yes? So what happens is, what happens on the next one?
Plus the
Plus
the 2 factorial.
2 factorial over, this is over 1 factorial, isn't it?
Yeah.
This is over 2 factorial x squared. So what's going to cancel? What's going to happen? Those are going to cancel. What's the next one going to be? Minus 3. This is 3 factorial over 3 factorial x cubed. So those cancel.
Oh.
What's the next one? Plus 4 factorial over 4 factorial x to the 4th. So what keeps happening is that this function becomes 1 minus x plus x squared minus x cubed plus x to the 4th, and is an alternating function.
Oh.
Everyone okay with that? Or rather, this function is what? The sum. Can we write the equation of that as we go from 0 to infinity?
It's like alternating.
It's just an alternating, so it's negative 1 to the
Negative x to
the n minus 1.
No,
Or plus 1.
0.
What?
It's just
Oh, first one's 0. Okay, thank you. Right? Times x to the n, isn't it?
Yes. Could you just like put it
Wait,
like
where's
a
your
geometric
factorials?
sequence that like has a ratio of negative?
Oh, let's start to see that this could be a geometric sequence. It's a geometric sequence. What geometric sequence? It's the sum of, can we put these together?
Yeah.
That's negative x to the n. Because what's happening each time?
multiplied by.
We're multiplying by negative x. Oh wait, we already knew that. What's the sum of a geometric series?
1 over.
A1.
The first term
A1
divided
over
by 1 minus
R.
the common ratio.
Oh.
No wonder.
If the common ratio is negative x,
Oh, what?
One of your
then this thing will add up infinitely to this.
That's whack.
All right, you want to? Here's mind blowing. No, not quite. Sorry, not quite there.
No.
Almost there. Yeah, do one more thing. We'll get to the bottom. It's almost. We're gonna make it into the harmonic in a minute,
Oh.
Why not?
but not yet. First, let's do another function that we like. So this is one of the functions we're gonna use, but there's gonna be others. So, can I erase this? I'm gonna leave the Maclaurin series part up and the formula. We can do that again. Let's try sine of x. Now, this isn't actually that bad because what happens with all the derivatives?
What's
Just
sine?
alternate.
Oh.
Sorry, it's on video.
It's true.
All right. So what is f of x? That's sine x. What's f prime of x? Cosine x.
Yes.
Oh, sorry. Yeah. No.
Wait, are we just
I went the wrong way. Sorry. F prime of x is cosine x. What's f prime of x? Negative sine x. What's f prime of x? Negative cosine x. And then it's going to start repeating, isn't it? Right? Because that's going to be sine x, and it's just going to keep going. All right. For now. Yes. What I would do from here is I would do a ratio test to figure out where to converge. We'll come back to it.
A ratio test?
Why would you just use a geometry?
So what we ended up with? What we ended up with right here is what? It's a power series. It's just like I could have given you this one on the test today, right? And you would have said find the radius of convergence.
Yep.
Right? And you know how to do that already. Right?
Sure.
Okay.
Now, what's f of 0 here?
Stop flexing.
It's gonna be 0.
Sine of 0 is 0. Good. F prime of 0. Cosine of 0 is 1. F prime of 0 is 0. F prime of 0 is
-1.
F the fourth of 0 is 0, and it's just going to keep repeating, right?
Isn't that like an oscillating thing?
No, because this is just the coefficients. All right. So let's build our Maclaurin series.
What, you jealous of me?
I'm sure I am.
You should be.
Let's build it. So I claim that sine of x is equal to f of 0, which is 0, plus f prime of 0, which is 1 over 1 factorial times x, plus 0 over 2 factorial x squared, minus 1 over 3 factorial x cubed, plus 0 over 4 factorial x to the fourth, plus 1 over 5 factorial x to the fifth, plus 0 over 6 factorial x to the sixth, minus 1 over 7 factorial. I haven't written all these down, but I know the pattern now, right? What's the pattern going? It's going, this is 0 over 0 factorial x is 0. So it's 0, 1, 0, negative 1, 0, 1, 0, negative 1, etc. What do we notice about all these? If something's 0, then what's going to happen to it? It's going to go away. So sine becomes x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh, etc. Why does it make sense? Tell me about all these numbers.
Odd numbers.
They're odd. Tell me about sine as a function.
It's odd.
It's an odd function, right? Going back to our trig identities, even, right? So sine is an odd function. Guess what cosine's going to be?
Even.
The evens, exactly. So cosine of x is going to be 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the fourth minus 1 over 6 factorial x to the sixth, etc.
So we're just approximating.
We're not. Here's what's crazy. I claim it's not an approximation if we go infinitely. If we can match infinitely all the derivatives of this function and make a polynomial that matches a perfect sine curve, right? Because what do polynomials do? Is sine a polynomial? Yeah. Is sine a polynomial? No, it's what? It's trig and it keeps going, right? And all the way down to the end, eventually, what's going to happen? It's just going to keep going. Whereas a polynomial, right? A polynomial is going to what?
Reverse.
Okay.
So the polynomial is going to what? The polynomial is going to end, isn't it? So the polynomial eventually, a polynomial goes, even if you make it like really squiggly, eventually it like goes that way and goes that way, right? And somebody said it. That means depending how far I go on my derivatives, I can match this sine curve pretty well. But eventually they're going to what? Split apart. They're going to diverge. They're going to move away from each other.
Oh, that
Right?
me. I'm a second.
So if we can figure out an interval of values over which they match, or if they're diverging over here, then in here they're what? Converging. We can figure out an interval, I know you can read this, of convergence by using the ratio test over which this polynomial is exactly this sine function.
If you make it
Why
infinity.
do-
Wait, could you repeat
why
that?
do you need
Oh, interval.
Ah,
Oh no.
So if we can, it depends on, we'll do the ratio test. So some of these will only go like from 0 to 1 and -1, like we saw a lot, right? But some of them will be infinitely large, right? Where we can actually say, is a sine curve a polynomial?
No.
It is.
Over certain
It's
intervals.
an infinitely long polynomial with an
Oh.
of an infinite degree. Because what's going to happen? Look, the degrees keep getting bigger. 5, 7, 9, 11, 12, 137, 2,700,655,000, blah, 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 3, whatever, right? Like,
Wow. What an average.
But on this, so you're saying in this one that eventually diverges, it's like this polynomial format for a little bit, and then when it begins to diverge,
it depends how far down the chain we'll go. But if we go all the way down the chain, if we do an infinite number of polynomials added together, we create this sine curve. I would even claim that every function could just be built out of an infinitely long polynomial where we're matching the derivatives, right? We're matching the derivatives so that we create the polynomial that's perfect.
What if it's not continuous?
That's probably going to diverge.
But like, if it's not continuous, how do you get like out of that? You don't even get that first step.
That's a good question. Amy wants to know, well, shouldn't I be able to take a derivative? Like, for example, the derivative of sine should be what? Cosine. What's the derivative of x? 1. What's the derivative of 1 over 3 times 2 times 1? X cubed. 1/2 x squared. What's the derivative of 1 over 5 times 4 times 3 times 4 times 5?
Oh no.
So this is the derivative of that. Right? Now, what's the sine of 2?
It's not.
Sine of 2. Does anyone know how to do the sine of 2 without a calculator?
no.
Now we do.
Oh, you still can't
Because
do
I
it.
can plug into this and figure out numbers
What?
without having a calculator.
Does the
You're
Arabic
adding
thing
infinite amount, you still don't know.
So I can't add an infinite amount. But how about this? This is an alternating series.
Is there like
Hold on. Shh. This is an alternating series. So if I wanted, let's say I wanted the sine of 1, right? Wouldn't the sine of 1 be pretty close to 1 minus 1/6 plus whatever, 1/120th or whatever that is, right? If I stop there, let's just say I use the first 3 terms.
Percentage.
How far off am I?
Less than the next
Less
term.
than the next term. 1 over 7 factorial is a ridiculously small number. So we are, just by adding 3 numbers together to get the sine value, we are really, 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 really close. Because 1 over 7 factorial is a tiny number.
5,040.
So 1/5. See, I told you, big brain. Right? So 1 5,000.
We're not saying big brain. We said like.
All right, I'm a big idiot, but that'll kill you.
Thank you.
But 1 over 540. Shh, focus.
Julian Jenner.
1 over 5,040. I take those odds, right? If you tell me you're within 1/5,040th, do you know how the calculator calculates sine?
It does exactly.
It does this.
No.
It plugs it. It plugs into
No.
this equation.
Please don't.
The way you word things
I
nowadays.
didn't know that.
Now you know.
I did.
All right. Let's do one more. So we learned 1 over. Shh. I know it's late. I know you guys are doing awesome. I'm so proud of you. Thank you for being here and doing all this. Right, Jimmy. One more. So, yes.
So for the interval of conversion, are you saying that not every single x will work for the whatever thing that you
Yeah, I'd have to figure out which x's I could plug in to use this. So some of them won't go all the way to infinity. Well, so some of these will actually end up being approximations instead of exact. We'll get there. These ones I'm telling you now are exact. 1 over 1 plus x. Sorry, that's not true. 1 over 1 plus x, the one we did first, that's only going to go, we know that we just did it, we did it at 0, right?
Mm-hmm.
So at 0. If we go to -1, it's not going to work anymore. Why? Yeah. So that one we can actually tell that we're not going to be able to go past -1 because then it's going to give us a problem.
Oh, which is
With sine and cosine, it's actually an infinite interval convergence, and you can do the math. But let's do one more. The last one is e to the x, one of our favorite functions.
It's so perfect.
Right? This one's actually really easy. I know, right? We're almost there. We're there. Watch. Here it is, Ben. Here it is. So, Alex is so excited. He's like, I knew I should have come tonight. All right. So,
He almost did.
the nice thing about e to the x is f of x is what?
easily
F prime of x.
And what's f prime of x?
e to the x.
Yeah, so what's nice about this, let's do the Maclaurin series here too. We're doing the Maclaurin series a lot because the Maclaurin series is easy. We could plug in any value, it doesn't have to be 0, but 0 is easier. So f of 0 is what? 1, f prime of 0 is 1, f prime of 0 is
1.
Right, you got it, right? Alright, so when we build our series, let's use our formula. This is our formula down here, right? So we're going to use this formula down here. Okay, so I claim that e to the x is equal to the first term, which is 1, plus f prime is 1 over 1 factorial x, the first, plus 1 over 2 factorial x squared, plus 1 over 3 factorial x cubed, etc., right? We all see what's going on here?
Yeah.
What would the equation for e to the x be? The sum of e to the x would be the sum from 0 to infinity of 1 over n factorial x to the n. Yes? Yeah, we've done this. This we can find the interval convergence on. It's not that hard. So, what's interesting is, you start to see that this isn't unlike these, is it? No.
It's just not awesome.
Well, what would happen if I plugged in I pi
Why would you want
Oh,
to this?
Oh no.
because I to the 4.
You're gonna
What
get
is
-1.
Yeah, if I plug in I pi,
I
I is the imaginary number, right?
Helen.
So
I-
e to the I pi would be 1 plus I pi plus 1 over 2 factorial times
Oh,
I pi quantity squared.
Wait, is the I? What is
Just because it's fun.
Like
is I just a number?
root
Now, what is
-1.
I?
The square root of -1.
Square root of -1, right?
Yes, I did.
Now, what's going to happen here?
Oh, it's just -1 over.
Yeah, I squared is -1, so this becomes
Negative.
negative. Becomes that.
Because.
Then the next one would be plus 1 over 3 factorial I pi cubed,
That's just negative I.
right? I pi cubed is negative I, so this is negative I times pi cubed,
Yay.
right? And then the next one would be plus 1 over 4 factorial. I to the 4th is 1, so this is pi to the 4th. So what you see here is that I lost it. Ah, crap.
Dang it.
Well, you're seeing the alternation now. It's these added together. It's sine plus cosine.
Yes.
And if we just subtract the I lost it. We'll do that later. I don't want to keep you. So all right. So that's it. That's all I got. So I'll figure it out. I'm sorry, Alex. I know. I'm sorry. I'm sorry. I lost it. It's late. I lost it.
Not gonna be able to.
9 months.
You gotta solve it.
Yeah, not gonna be able to.
Well, this is
It's like one of
all
those
right. Well,
like,
this is
episodes, like characters
this and this and this. Those are all the cosine of pi, aren't they?
What?
Right.
Yeah. Sure.
Yeah, right. Yeah, that's the there we go. Okay, that's the cosine of pi. And then these are the sine of pi. Oh, that's it. I got it. These are the sine. All of these are the sine of pi times I, because each of them is multiplied by I. And so what you end up with is, and this is going to really throw you guys for a loop. This is really fun. What this ends up with is, so I claim that e to the I pi is equal to cosine pi plus I sine pi.
Oh.
And that is cis
No. Bro. What
pi.
Oh,
Do you remember cis from last year?
No.
Cosine plus I sine?
Yeah, bro.
Right? That
Yeah,
is the
bro.
imaginary number in polar form. The imaginary polar form in the pi direction, right? Which is we're going nowhere. We're going in pi direction. We're not going up and down, and that ends up being -1.
Oh.
So we go 1. It's 1 cis pi. So that means e to the I pi is -1, which means e to the I pi plus 1 equals 0.
Whoa.
Which is useless and beautiful. All right. So thank you all for doing that.
Spread.
What your homework for Tuesday is going to be on these basic functions and building them. So all you're doing is you're taking a bunch of derivatives so you see a pattern, and then plugging in the value that you're centered at, and then writing the equation. If you look in the book, there's a beautiful, nice, neat
No, I do that.
equation for this right here on page 543. So right before your homework, there's a beautiful, neat equation for this that you're going to love. Thank you. Seniors, we're going to get you where you need to be, okay, before in the next 3 class days. Okay, I promise. Right, and then we'll all be ready for the AP, and you guys are going to do great. You people are going to do great too. Way to go, you people. The video.
Watch the entire video. Delete.
That'd be terrible.
That'd be so fun.
Thank you.
Oh yeah.